This is our second video about hyperbolic functions. In this video, we'll discuss the nicknames for the hyperbolic functions, or a few of them. We will derive the differentiation rules for a few of them, and then we will use a memory device by comparing these derivative rules to the derivative rules for our trig functions. We'll look at the corresponding anti-differentiation rules, and we'll do some examples of derivatives and antiderivatives involving hyperbolic functions. So before we get started on that, let's briefly review what we talked about in the last video. The hyperbolic sine of x is this odd combination of e to the x and e to the negative x. Hyperbolic cosine, it looks almost identical. Instead of having a minus sign there, it has a plus sign there. Hyperbolic tangent of x is defined to be hyperbolic sine over hyperbolic cosine. And the hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent are defined in exactly the way that you would expect using trig, your trig identities. We know that cosecant is 1 over sine, so hyperbolic cosecant is 1 over hyperbolic sine. Secant is 1 over cosine, so hyperbolic secant is 1 over hyperbolic cosine. And hyperbolic cotangent, or cotangent of x is 1 over tangent, so hyperbolic cotangent of x is 1 over hyperbolic tangent of x, which is the same as hyperbolic cosine of x over hyperbolic sine of x. In the last video, we also looked at the graphs of these first three functions. We said if we look at the limiting behavior, the end behavior of this, as x goes to positive and negative infinity, what we see is this. As x goes to infinity, hyperbolic sine of x goes to infinity. As x goes to negative infinity, hyperbolic sine of x goes to negative infinity. But it goes to negative infinity and positive infinity in an interesting way. As x goes to positive infinity, this term approaches 0, and that hyperbolic sine function approaches the function y equals 1/2 e to the x. That's that right there. As x goes to negative infinity, this part goes to 0, so the function approaches a negative 1/2 e to the negative x. So we see that right there. It's almost like an asymptote, but it's not quite because it's a curve rather than a line. The hyperbolic cosine is similar, but it approaches 1/2 e to the x and positive 1/2 e to the negative x on either side. And we also evaluated these functions at 1, and we saw that hyperbolic sine of 0 is 0, just like sine of 0 is 0, and hyperbolic cosine of 0 is, well, that's 1 plus 1 times 1/2, so we get 1. So hyperbolic cosine of x, or of 0, is 1, just like cosine of 0 is 1. And hyperbolic tangent, if you write it in terms of exponentials and you take some limits, you see that the graph looks like this. As x goes to infinity, y approaches 1 on this graph. And as x goes to negative infinity, the hyperbolic tangent approaches -1. Not sure about the concavity. Then we proved, just using the definitions of the functions, that the hyperbolic sine is odd, hyperbolic tangent is odd, and hyperbolic cosine is even. And we talked about the fact that these functions behave in a very similar way to the way that trig functions behave. The cosine of t and sine of t are parametric equations that will trace out that unit circle. So as t increases, you go around and around that unit circle. If we look at this hyperbola given by x squared minus y squared equals 1, it turns out that the hyperbolic cosine function and hyperbolic sine functions, those trace out this curve as t increases. We'll talk more about parametric equations in Calculus 2 and in Calculus 3, but the idea is for every t value, this x can be given by hyperbolic cosine of t, and y can be given by hyperbolic sine of t, and we're going to trace out points on this curve. So where cosine and sine trace out points on the unit circle, hyperbolic cosine and hyperbolic sine trace out points on this hyperbola. So when you remember that, this identity makes a lot of sense. You can also verify it algebraically. Now, if you try to remember this by comparing it to your trig identities, you're going to have problems because your trig identities often have the wrong SIGN signs. and it's because the trig identities are based on a circle, x squared plus y squared equals 1. The hyperbolic identities are based on a hyperbola, x squared minus y squared equals 1. But if I take this identity and I divide it by hyperbolic cosine squared, I get this one. If I take this and I divide it by hyperbolic sine squared, I get this one. And these are analogous to the Pythagorean identities from trig. Okay, so that's the overview of what hyperbolic functions are, what their graphs look like, and what their behavior is, and sort of what they're all about, why we call them hyperbolic functions in the first place. It's because the points lie on a hyperbola, if we think of those as parametric equations for x and y. All right, so I promised you we'd talk about the nicknames for hyperbolic functions. You can probably hear that it's difficult to say hyperbolic sine, hyperbolic cosine, hyperbolic tangent all the time. So people use nicknames for these. I don't tend to use them. I don't know why, but this hyperbolic sine of x is sometimes read sinh x. Hyperbolic cosine of x, I've heard it pronounced two ways, cosh x and cosh x. And then this one, hyperbolic tangent, I've heard it called tanch x, but I always just heard this is sinh and cosh. And then recently, this last year, I had a student tell me that this was pronounced tanch x, but I was always told that it didn't have a pronunciation because it's like tan. It sounds like it's not a language from this land, right? Tan. So we don't really have nicknames for all of them. So you have to say the whole thing most of the time. Hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent. I guess you could call that coth. I don't know what you'd call those. But the nicknames for these, standard nicknames are sinh x, cosh x. And I'm not sure if that's standard, but I had a student recently tell me that that's pronounced tanch x. Okay, so now let's look at some differentiation rules and anti-differentiation rules for these functions. First, we're going to derive the derivative rule for hyperbolic sine, and then we'll derive the derivative rule for hyperbolic cosine, just using those definitions in terms of exponential functions. It's really easy, because we all know how to take derivatives of exponentials. So if I want the derivative of hyperbolic sine of x, I can find that by taking the derivative using the definition. Now the derivative of 1/2 times a function is 1/2 times the derivative of that function. So I bring my 1/2 down, and then I take the derivative of each piece separately. The derivative of e to the x is e to the x. Then we bring the negative down. The derivative of e to the negative x is e to the negative x times the derivative of the inside. The derivative of the inside is -1, so we multiply by -1 and we get that. Well, that's the definition of the hyperbolic cosine of x. You guys can probably see what's coming. Here are our new derivative rules. The derivative of hyperbolic sine, if you prefer sinh, of x, is hyperbolic cosine of x, just like the derivative of sine of x is cosine of x. Isn't that convenient? Okay, let's look at the derivative of hyperbolic cosine. Can you guess what it probably is? If you said negative hyperbolic sine, you were almost correct. So hyperbolic cosine looks like this. Let's take its derivative. Bring the 1/2 down, bring that e to the x down, derivative of e to the x is e to the x, and the derivative of e to the negative x is e to the negative x times the derivative of the inside by the chain rule. The derivative of negative x is -1. That's hyperbolic sine. Notice it's in the exact same order as the original hyperbolic sine, so it's not negative hyperbolic sine, it's hyperbolic sine. So notice we have the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. It's almost like our trig rules. They're derivatives of our trig functions, but the SIGN signs are wrong. Both of these derivatives are positive. They are each other's derivatives. Okay, keep that in mind. And now let's look at the derivative of hyperbolic tangent. Well, I could find that derivative in terms of exponentials, but now that I know the derivative of hyperbolic sine and hyperbolic cosine, it's probably easiest to derive this formula in terms of hyperbolic cosine and hyperbolic sine, because tanh x is sinh x over cosh x. I don't like using those nicknames. I don't think I will anymore. So I've got the derivative of this quotient. Just use the quotient rule. It's the bottom function. Low d high minus the derivative of the top function. Derivative of hyperbolic sine is hyperbolic cosine. Minus, so it's low d high minus high d low. Derivative of hyperbolic cosine is hyperbolic sine. Over low low. So I have cosh x squared minus sinh x squared. Remember that identity. Hyperbolic cosine squared minus hyperbolic sine squared is 1. We proved that in the last video, and then we reminded ourselves of that at the beginning of this one. So that numerator is just 1. Did you guess it? What's the derivative of tangent? Hyperbolic tangent? If you said hyperbolic secant squared, you were right. It's exactly what you would expect. So the derivative of hyperbolic tangent is hyperbolic secant squared. Now I'm not going to derive the rest of those differentiation rules. Instead of doing that, I'm just going to tell you what they are. They're pretty straightforward. Given what we know about our differentiation rules for trig functions. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. When we change to the hyperbolic versions of those functions, hyperbolic sine, hyperbolic cosine, and hyperbolic tangent, the result is exactly what we would expect, but the hyperbolic sine, cosine, and tangent all have positive derivatives. The other three, that's the hyperbolic cosecant, hyperbolic cotangent, and what's that third one? Hyperbolic secant. They are exactly what you would expect, except that they're negative. The derivative of cosecant of x is negative cosecant times cotangent. So the derivative of hyperbolic cosecant of x is negative hyperbolic cosecant times hyperbolic cotangent. Make sure both of those have an x inside, otherwise it doesn't make any sense. You have to evaluate these functions at some value of the variable. These aren't angles. These functions aren't periodic, but we have to have an inside function for them to make sense. The derivative of cotangent squared is negative cosecant squared. Derivative of hyperbolic cotangent squared is negative hyperbolic cosecant squared. Derivative of secant is typically secant times tangent. So the derivative of hyperbolic secant is hyperbolic secant times hyperbolic tangent, but this time it's negative. Okay, so the rules are exactly what you would expect from your trig rules, except there's a sign difference, an SIGN sign difference. The first three, the hyperbolic sine, cosine, and tangent, are exactly what you would expect, but they're all positive. The other three are exactly what you would expect, but they're all negative. So now we've got 6 new rules, that we can use in combination with all of our other differentiation rules to find some derivatives. So let's say someone asks you to find the derivative of this function. We've got y equals x cubed times hyperbolic tangent of x squared. Well, first of all, I notice it's a product. So there's my first function and there's my second function. So I know I'll have to use the product rule. Derivative of a product is derivative of the first times the second undifferentiated plus derivative of the second function times the first undifferentiated. And the derivative of x cubed is 3x squared. And this derivative requires the chain rule. So we say, well, what's the derivative of the outside function? The derivative of hyperbolic tangent is hyperbolic secant squared. Evaluate it at the inside function, and then multiply by the derivative of the inside by the chain rule. That's 2x. And so I've got this times that x cubed. Don't forget the x cubed. And so we get 3x squared times hyperbolic tangent of x squared plus 2x times x cubed is 2x to the fourth times hyperbolic secant squared of x squared. And that's my y prime. Let's do another one. Let's say we want to find the derivative of natural log of, let's say, hyperbolic sine of e to the x. So this is going to require using the chain rule twice. I've got an inside function here. Now remember, whenever you're doing the chain rule, you have to identify the outside function first. And you're saying to yourself, what's the derivative of the outside function? That outermost function. The outermost function in this case is the natural log, and that's not a product. That's the natural log of this. This is not a product of three things, certainly. It's a natural log of this, which is the hyperbolic sine of that. So it's a double chain rule. Okay, so I say, what's the derivative of natural log of a function? It's 1 over the function times the derivative of the inside by the chain rule. Okay, then I look at this one and I say, what rule do I have for that? Sort of ignore this, I don't even need it anymore. Just focused on this derivative. Well, the derivative of that requires the chain rule as well because I've got the hyperbolic sine of this inside function. So I've got 1 over hyperbolic sine of e to the x times the derivative of hyperbolic sine of a function. The derivative of hyperbolic sine of a function is the hyperbolic cosine of that function times the derivative of the inside. And the derivative of the inside is just e to the x. So now I've got this times this, and that's an e to the x over 1. Or you could just bring it out front. Hyperbolic cosine times, or of e to the x over hyperbolic sine. If I multiply those straight across, I get, well, I brought that e to the x out front. I get hyperbolic cosine over hyperbolic sine. That's hyperbolic cotangent of e to the x. And so it turns out that y prime is equal to that. So let's do one more, last one. You're still asked to find the derivative And let's say someone asks you to find the derivative of this. Let's say you've got let's say hyperbolic secant of 2x cubed minus 1 over x squared. Let's make it a quotient rule. Divide by 2x plus sine of x. Okay, so according to the quotient rule, actually there's probably not enough space to do the quotient rule on this one. We'll use another sheet of paper. So we've got, this is our function. Oops, there we go. Low d high. Don't forget your parentheses because that bottom function has a lot going on. Got two terms. So I need another sheet of paper. It's going to be a long one. That's low d high. So the bottom function times the derivative of the top function. And I'm differentiating, so it will be helpful to rewrite that as an x to the negative 2. It's low d high minus high. And you can rewrite that again, or you can leave it as is. Either way is fine. I'm not going to do anything with it. That's high d low. All divided by low low. So it's that bottom function squared. All right, almost done. We just have to compute this derivative and that derivative. If we can simplify, we should. If we can't, we'll just leave it alone. Probably can't. It was so complicated that there aren't going to be factors in common, probably. So I'll bring this low function from our low d high down. And then I focus on this derivative. Now notice that's hyperbolic secant of something that is not a product, even though it kind of looks like a product. We have to take the hyperbolic secant of something. So this is the hyperbolic secant of this, which means we're doing a chain rule. The derivative of hyperbolic secant of something is, oops, hyperbolic secant has a negative derivative. It's a negative hyperbolic secant times hyperbolic tangent of the inside function. So both of those need to be evaluated at that 2x cubed minus x to the negative 2. It's derivative of the outside. Evaluated at the inside times the derivative of the inside by the chain rule. And the derivative of the inside is 6x squared. Negative 2 times that negative 1 is going to make it a positive 2. Then we'll multiply by x to the 1 less power. So I've got low d high is all of that minus high d low, derivative of 2 times x is just 2. Derivative of sine of x is cosine of x. And then we still have that low, that 2x plus sine of x quantity squared. So I have a 2x plus sine of x on both terms. I've got one on this term, but I don't have one on that term. So we're not going to be able to simplify it that way, but we could factor out a negative hyperbolic secant of this function. I've got one of those right here, and I've got another one right here. I think I'll do that. I don't think it's going to make it that much simpler. I've got negative hyperbolic secant of 2x cubed minus 1 over x squared times everything else. And we're left with a 2x plus sine of x times a hyperbolic tangent of x times this 6x squared plus 2 times x to the negative 3. I think I may have said the wrong inside function for that hyperbolic tangent. It's hyperbolic tangent of all of this. Okay, so that times that gave me my first term, which is very long and had a lot of factors. And then we factored out that negative, so we're left with a plus 2 and a cosine of x. Okay, so that's our derivative. We used one of our new rules plus the quotient rule. Okay, so we've got derivative rules. We had 6 of them. We're going to do each of these backwards to get an antiderivative rule. The antiderivative of hyperbolic cosine of x is hyperbolic sine of x plus c. Since the derivative of cosh x is sinh x, I still have trouble saying that. The antiderivative of sinh x is cosh x plus c, okay? Derivative of tan or tanh x, sorry, my jokes are so bad, is hyperbolic secant squared x, so the antiderivative of hyperbolic secant squared x must be hyperbolic tangent of x plus c. The derivative of hyperbolic secant of x is negative hyperbolic secant of x times hyperbolic tangent of x. Now, when we state our rule, we usually multiply both sides of this by -1. So we take the antiderivative of this, and that's negative hyperbolic secant of x plus c. Okay. That's secant. Let's look at cosecant next. The derivative of cosecant, or hyperbolic cosecant, is negative hyperbolic cosecant of x times hyperbolic cotangent of x. So the antiderivative of hyperbolic cosecant of x times hyperbolic cotangent of x is negative hyperbolic cosecant of x plus c. It's just, these are just these rules backwards. I almost don't want to write them down because they're sort of obvious. But it's just, if the derivative of this is this, then the antiderivative of this is this. The derivative of hyperbolic cotangent of x is negative hyperbolic cosecant squared of x. So we've got the antiderivative of hyperbolic cosecant squared x is negative hyperbolic cotangent of x plus c. Now, if this feels like a lot, I know it's like you just had to learn 6 new rules, but hopefully it's not too bad if you remember the relationship between these and your trig rules. These are just exactly what you would expect using your trig rules. Just add that extra word hyperbolic to the to both sides of that statement that you're saying this is equal to this. But you have to remember that the signs are sometimes different. The derivatives of hyperbolic sine, cosine, and tangent are all positive, and then the other 3 are all negative. Okay, now in practice, we usually don't just work with functions that look like this. maybe instead of an x, you have a kx inside, and you have to do those kx modifications that we talked about. And sometimes we have to do u-substitution as well. So we've got these 6 new rules and u-substitution, and that will allow us to anti-differentiate a bunch of other functions. Let's see. Now, we don't have rules for these, but the hyperbolic cotangent, and hyperbolic tangent, you can come up with rules for these by writing these as hyperbolic cosine over hyperbolic sine, and hyperbolic sine over hyperbolic cosine, and doing a u-substitution. If you do the u-sub, since the derivative of this is this, we end up with natural log of the absolute value of the denominator in both cases. So you can memorize those as rules if you prefer, or you can just derive them every time. Or you can do like I did and not have it memorized, but write it like this and then quickly remember how that derivation comes about. The denominator is my u, so I end up with natural log of the absolute value of u plus c. Okay, so we've got those 6 antiderivative rules, and then these that come from u-sub. Let's look at some antiderivatives involving hyperbolic functions now. Now here is the idea. If you can antidifferentiate this function that has trig functions in it, you can just as easily antidifferentiate the same thing where there's just a hyperbolic function instead. This is sine squared x times cosine of x dx. Now, if you're looking at this and if you want to antidifferentiate it, the first thing you always ask yourself is, do I have a rule for that? And we don't have a rule for this because it's a product. But we do have u-substitution. And remember, we want to use u-substitution every time or anytime we see a function nested inside another function. At least that's the most advanced technique we have at this point. Now, it's not obvious that there's a function nested inside another function here, but actually there is. Remember what this means. If you see a trig function and there's some number as a subscript here, or I said subscript, superscript, looks like an exponent. What that really means is we're taking that trig function and we're raising it to that power. Unless it's a -1, then it's an inverse trig function, and I hate that notation because of that reason. I know there's very strong words. Shouldn't use the word hate, but you get the idea. I don't like it. But if this is a number other than -1, we interpret that as a power. That's really what it is. So when I see this sine squared x, I immediately translate and I say, that's really this. And this looks like an excellent candidate for u-substitution, because now I've got a function squared and the derivative of that function over here. So I would choose u to be sine of x. The derivative of u is cosine of x dx. So now I can write that as u squared times du. So I've got a u squared and a du there. And now my integral is written entirely in terms of u, and I can antidifferentiate that, right? I've got a rule for that. So we add 1 to the exponent, we divide by the new exponent, don't forget to add c. And then we replace u with this trig function. Now standard notation is not this notation. This is just that convenient notation for just helping me remember that there's a function nested inside another function there. This is standard notation. And the parentheses aren't even really necessary around the x. So if I've got 1/3 u cubed plus c as my answer, this becomes this. U is actually sine of x. And when I mean to cube sine of x, I don't write sine of x in parentheses quantity cubed. That's standard notation. We write sine cubed x plus c, and that's our answer. That's just a u sub with some trig functions. Now, if you can do that, you can do this. It's exactly the same thing. Exactly. It's instead of having a sine of x, I have a hyperbolic sine of x. And instead of having a cosine of x, I have a hyperbolic cosine of x. But I treat it exactly the same way. So I see I've got a hyperbolic sine function being squared. It's multiplied by a hyperbolic cosine function. So if I let u be my hyperbolic sine function, du is hyperbolic cosine of x times dx. So that's du. This is u. It's the same thing. I hope you're playing this YouTube video at like 1.75 speed because you've just seen this. We just did this a second ago. It's the same. So I get 1/3 u cubed plus c when I antidifferentiate, and then I back substitute. The only difference is when I back substitute, I'm substituting hyperbolic sine of x rather than sine of x. So if you can do this, you can do this. It's the same. Let's look at another example. Let's say somebody gives you this problem. You've got hyperbolic secant of the square root of x times hyperbolic tangent of the square root of x divided by the square root of x dx. Now that looks hard, but it's actually not too bad. You say to yourself, do I have a rule for that? No, we don't have a quotient rule. So then we say, okay, the only advanced tool we have at this point is u-substitution. So it must be a u-sub. I'm looking for a function nested inside another function. Square root of x is inside those trig functions, or not trig functions, those hyperbolic functions. So I will write that u is equal to that inside function square root of x. I'll call that x to the 1/2. And then I differentiate this, and my hope is that when I differentiate this, I will get something out of this derivative to address that square root of x in the denominator. Otherwise, it's going to be a problem. So we compute du. That's 1/2 of x to the 1/2 minus 1, which is negative 1/2, times dx. And that simplifies. That's 1/2, and that's a square root of x in the denominator. So I've got a 1 square root of x dx there, and there's this extra 2 here. It's in the denominator. I'd like to get rid of it, so I'll multiply both sides by 2. And now I've got that. So this integral becomes hyperbolic secant of u times hyperbolic tangent of u. Oops, there should be an h there. You don't really even need the parentheses because it's just a single term. And then this 1 square root of x dx, there's an implied 1 over that because it's in the denominator. That's really a factor of 1 square root of x dx. That's equal to 2 du. So I'll put a 2 out here and a du over here. And then I bring my 2 down. The antiderivative of hyperbolic secant times hyperbolic tangent is negative hyperbolic secant plus c. Substitute your u back in, and then don't forget to back substitute. U was square root of x. Not too bad. That's our answer. Okay. So that is how we differentiate and anti-differentiate our hyperbolic functions. We've given our hyperbolic functions some nicknames: sinh x, cosh x, tanh x. We don't really have ones for this, like I don't know, cough. Yeah, it just does not sound like it's from this planet. Or you could just keep saying hyperbolic cosine, hyperbolic sine, hyperbolic secant, like I do. Just to review, let's review again. These are the graphs. They come from taking limits of these functions as x goes to positive and negative infinity, and then you can see that the hyperbolic cosine and hyperbolic sine graphs approach the curves given by y equals 1/2 e to the x and y equals negative 1/2 e to the negative x, y equals 1/2 e to the x, and y equals 1/2 e to the negative x for the cosine case. If you take a ratio of those two and you take some limits, you find these limits for your hyperbolic tangent. Hyperbolic sine and hyperbolic tangent are odd, hyperbolic cosine is even. You could use these to determine the even and odd properties of these guys if you wanted to. What makes them hyperbolic functions is that hyperbolic cosine and hyperbolic sine satisfy this equation. Hyperbolic cosine squared of a number minus hyperbolic sine squared of the same number is equal to 1. So that means that if x equals hyperbolic cosine of t and y equals hyperbolic sine of t, so that x and y are positions in the xy plane, and as t increases, they're tracing out some curve, that point lies on the graph of a hyperbola. If we did the same thing with cosine and sine, that point would lie on the graph of a unit circle, x squared plus y squared equals 1. So the trig functions are related to circles. The hyperbolic functions are related to hyperbolas in a similar way. And if we take this identity and divide it by hyperbolic cosine squared and hyperbolic sine squared, we get a couple of other identities as well. Okay, now let's review our derivative rules. Got 6 of them. They're just what you would expect. Actually, let's look at that chart I made with the antiderivative rules on it. How did I lose that? There it is. All of our new rules right here. Since the derivative of sine is hyperbolic sine is hyperbolic cosine, this is the antiderivative. There's that rule, that rule, that rule, and that rule, and that rule. Do all of those backwards and you get these rules. Now these are easy to remember if you know your trig derivatives. They're exactly what you would expect, but the hyperbolic cosine, sine, and tangent all have positive derivatives, and the other 3 all have negative derivatives. And then when you do that in reverse, it's exactly the same. Just multiply both sides of this equation by -1, and that's what you end up with, those antiderivatives over there. So you've got these 6 rules. Now these are not rules that come from the derivative rules, but we know how to do u-substitution now. So there's no reason that you can't take the antiderivative of hyperbolic cotangent or hyperbolic tangent of x by using these identities. Ignore those problems from a different video. Okay, now we put those together with u-substitution and our basic rules, and we get antiderivatives that look like this. Actually, let's do one last example. Let's do a kx modification of one of these. So let's say somebody asks you to find the antiderivative of 5 times the hyperbolic cosecant squared of 2x. Well, the antiderivative of hyperbolic cosecant squared is negative hyperbolic cotangent. So we'd get -5 times hyperbolic cotangent, oops, there's an h there, plus c. And inside, we would still have that 2x. But since there was a kx inside, we have to divide by the k. So that is, if I take the derivative of that, I'm going to get that back. It's going to work out just fine. So that's our last example. And that's it for derivatives and antiderivatives involving our hyperbolic functions.